Greetings. In this video, we are going to look at beams. We will talk about different beam types, beam strength, and the different ways that beams might fail. So, in general, a beam is a structural element that is capable of withstanding load primarily by resisting bending. Bending or flexure is the term. Flexure, F-E-L-X-U-R-E, flexure. The beam is loaded transversely or perpendicularly to its axis. All right, so this is the axis running left and right, or east and west, however you want to describe it, and it is loaded perpendicular to the beam's axis. Okay. Also, a bending moment exists in the beam that has to be addressed, and that's what we see here. These rotating. It's of course we know that the bending moment is the tendency for something to want to rotate. So once a beam is loaded, a moment is created around that support. It has a tendency to want to rotate. All right, some simple, straightforward beam loading situations. So here we have the beam loaded single point, so concentrated loads at the center, an intermediate location, not the center, two equidistant points, so they're the equal distance from the supports here, the same over there, and then the uniform load, which is the string of arrows that are connected together. So a couple different setups for how a beam might be loaded. All right, different types of beams. The simply supported beam is the most simple arrangement, as it says. The beam is supported at each end and the load is distributed some way along its length. So these are the supports here, and this is what the free body diagram looks like everything's been stripped away. So that is the simply supported beam. Couldn't be easier than that. As opposed to the continuous beam, which rests on several supports, at least three. So down here we see three simply supported beams, and we can see right here the connections or the breaks. And then here for the continuous beam, we run right over those supports without breaks. Okay. The cantilever, so this is kind of a third variety of a beam. We have the simple, the continuous, and the cantilever. So a beam supported only at one end. It carries the load to the support where it resists moment and shear stresses. Okay, so that cantilever is right back here. So here's our cantilevered beam right there. And it comes back and ties into this column. And then right at that location, beyond that lumber that we can't see, a moment is occurring. This beam is being pushed down. And a moment, a tendency for this to rotate about that point is occurring. And shear stresses as well. So the beam is being pushed down where the column is pushing up. So there's also shear occurring right at that same location. Okay. Allows for the overhanging of structures without external braces. That's a good thing, and can be constructed with trusses and slabs as well. So it's not just beams, trusses and slabs as well. All right, so there are two different types. There's the full moment connection, like a horizontal flagpole bolted to the side of a building. You could even think of a normal vertical standing flagpole kind of as a cantilever in that same regard. So that's here. This is the full moment connection. So right back there. So it is the flagpole that has been pinned back to the building, and that's a full moment connection occurring right back there. Or these two varieties on the right are created by an extension of a simply supported beam, such as we find on a diving board, and it extends over the edge of the swimming pool. All right, so this, well, not exactly a diving board, but pinned back at the wall right there, pinned back at the wall, and if it ended right here, it would be a simply supported beam. Same with this. If this guy ended right here, simply supported, but we extend it and we get that little cantilever space right there. All right, so both of these are pinned at the wall, and then both of them cantilever beyond. So here's a beam, and it's cantilevering beyond the beam, and a spring for some reason, kind of like a diving board, extending as well. Okay, so bending or flexure characterizes the behavior of a slender structural element subjected to an external load applied perpendicularly to the axis of the element. Okay, so the behavior of a slender structural load. So slender one of its dimensions is a small fraction, typically 1/10 or less of the other two. So it's basically just dimensions. So slender is a word that structural engineers use, and it's defining the depth of the beam essentially. So the beam depth and the beam width might be similar to each other, but they are a lot less than the beam's length typically. So that's why they're calling it slender there. So uniformly loaded, string of arrows, and here's our simply supported version right there, right? We got the two supports at each end, and here is a continuous beam actually with two cantilevers. All right, so being, yeah, I'm not technically sure actually whether you call this simple or continuous. Actually not sure what the, to be honest, what the answer is to that. It's a simply supported because it only has two of them, but so yeah, I think if we just flip right back real quickly to our yeah, so a continuous beam has at least 3 supports. So therefore I would not call this a continuous. I'd call that a simply supported beam with extended cantilevers. And then you could see it's kind of subtle, but here we have the whole kind of the smiley face kind of sagging, and here it's a little more complicated where we're sagging at the tip and then we come up over the support, we sag again, back up over the support, and down again. Okay, actually we were on this slide, but we covered it, so now I'm going to jump on to the next and we'll talk about deflection, which is something that is expected and allowable by code. Basically, code will say so here, and again, I've kidded before, but often whenever the question is what determines something in the world of structural engineering, it's building codes, it's span. Those are 2 big ones, and loading conditions. Three big answers to when something a determining factor. Okay, so deflection, the degree to which a structural element is displaced under load. So we expect wood floors to bounce a little bit. That's permissible. And the building code will tell the engineer you're allowed to let this thing bounce by about a 400th or 600th of an inch. So not allowed to move a lot, but a little bit's okay. So if we have a 40-foot beam span and it's permitted to deflect 1/400th, then a 0.1, so at 1/10 of an inch deflection is allowable. Okay, so that's permissible by code. Okay, under the load, the original length of the beam is slightly reduced to enclose a smaller radius arc at the top of the beam, resulting in compression, while the same original beam length at the bottom is usually stretched and is experiencing tension. Compressive forces are greatest at the top and tensile forces are greatest at the bottom. All right, so here is our beam, simply supported, 2 supports. And this is unloaded. There's no indication that it's being loaded. And then here comes the force. It is deflecting. And what this is all saying here is that the original length of the beam is slightly reduced under load. So as again, I go back to the racetrack as an analogy. So if this were a continuous big racetrack, this beam, the inside is shorter than the outside, right? Whenever we have a curved surface, and it's true of these beams because these are perpendicular. So this line right here is shorter than this line here. Okay, and it is experiencing compression. It's being crushed in and in. It's getting pushed in at the top, and then at the bottom, it's getting pushed out. And let's see, we will see those. We'll see some arrows coming up. Oh, here are the arrows. So at the top, the outermost top face is experiencing the greatest amount of compression, and then at the bottom face, it's experiencing the greatest amount of tension. Okay. And a beam has a neutral axis right through the middle, and here it is experiencing neither compression nor tension. All right, so that's that line coming right through there, roughly in the middle. So greatest tension at the outward face and the bottom, and then the tension reduces until it hits 0 at the neutral axis. Compression's the greatest on the top face, and it's getting reduced till it hits 0 at the neutral axis again. Okay, so here we have two simple beams, 1, 2, and here we have a two-span continuous beam, 1 continuous beam. Okay, so we have two beams, simple beams, broken right there. Here are our supports, 1, 2, and 3. They are both being loaded, center span, and they are experiencing compression at the top and tension at the bottom, just like we saw in the previous slide. Okay, now here when we jump down into the continuous beam, it's getting a little more complicated, and you need to understand this now. So here are our supports, 1, 2, and 3. So the beam's behavior is more complicated because it's a continuous beam. So we are coming down under load, right here, under load, coming down. But then when we are heading back to this support, we actually get inverted. And now, and so we're going to we'll talk about in the video concave up or concave down. So this is a concave up, and then here we go to concave down, and then back to concave up. So smiley face, frown, smiley. So concave up, concave down, concave up. And when that happens, very, very important, is that the tension in the beam actually moves from the bottom to the top. Right down here, we're experiencing tension at the bottom of these beams. So we can't simply say that all beams experience tension at the bottom. A continuous beam, the tension is moved to the top of the beam over the support actually. So tension down here at the bottom, tension down here at the bottom, just like we're seeing here. But here, the tension is moved to the bottom, and the compression, the tension is moved to the top, and the compression has actually moved to the bottom. Okay, and then here we go into a 3-span. So we have 4 supports, 1, 2, 3, and 4, and we see the outside behaving similar to the last, outside behaving similar, but now we don't have, I think this would all depend on the actual design of a beam and the actual span here. I think this is kind of perhaps simplified to make a point, which is fine. So here, the entire beam from the middle supports, all in tension here, all tension across the top, all compression at the bottom. Okay, so a slightly different variation there. Okay, let's talk about some beam failure modes. All right, 3 ways that beams fail: bending, vertical shear, and horizontal shear, all depicted here. Bending, vertical shear, right there, up and down, and horizontal shear, moving left to right. Bending, most common type of failure. Fibers along the bottom of the fibers along the bottom face of the beam are in tension, and those at the top are in compression. Most beams will fail in tension. That's typically the tipping point, is in tension, and especially concrete and masonry beams will fail very quickly in tension. So typically we will see cracks appearing at the bottom of beams, and that's what we see happening here. So this guy should obviously have glasses on. This is not safe here. But this is a bending failure, this beam right here, the bottom. So this is like a glue laminated timber built up of several plies, but it is a tensile failure at the bottom of the beam. Okay. Vertical shear happening right here. All right. An idealized mode of failure. So we don't typically see beams just shear so clean and crisp the way that it's depicted here. I think that's why they would call it an idealized mode. Tendency for a short beam to fail in this manner. I think this is a good vertical shear, though. You know, it's not perfectly vertical like this, but I think this is a good one. So the beam is pushing down and the column is pushing up, and that is a shear crack occurring right there. Okay. And a horizontal failure, which we see here. And again, going back to a glue laminated beam which we may see such a failure occur in. So these are plies. These are built up of many different plies, about a dozen plies. We would call that just the way a piece of plywood is built up of numerous plies. This beam is built up just the same. And right here, that little edge, that little shadow we're seeing there, that's because these internal layers have slid past each other. So that's a failure occurring right there. Okay, horizontal shearing. Okay. And one more here, horizontal shear. So frequent mode of failure, which should not be confused with checking in wood beams, right? When we get to wood, we will be talking a lot about different defects in wood, naturally occurring and otherwise. And so these could be horizontal shear failures, actually, and not checking. Here's checking. Usually runs along with the rings, essentially. It starts at a ring and kind of follows it there. So a check is kind of like a crack, but it doesn't go all the way through. And it typically follows the wood's annual growth rings, which are those light lines there. So here we see, again, a built-up glue laminated beam. I could see a line running right there, another there. Perhaps that's one, perhaps that's one. And so these might not be checks. They might actually be horizontal shear failures, where these things are being pushed left and right past each other. Okay? All right, and just let's take one look at how we might test deflection in a beam and different shapes of beams. Very important. So here is our scale, basically, to load the beams, and the beam is up here at the top. Okay, and that's the beam right there. So this, we see beam, and that's the top piece right there. The dial gauge is telling us how far the beam is deflecting, essentially. Okay, and that's what that's measuring right there. Okay. So this chart, kind of interestingly, begins to tell us about the importance of shapes, and we will see a lot more of this in the generals video. So here, coming across the top, we have the different beam types. So we have an I-beam, which I see right there, a flat piece of steel right there, a square piece of steel right there, wood here, and a channel on the left. Okay, and then we are loading them, and the channel was perhaps not tested, I would guess. I'm not sure why that's left like that. Let's take a look at the wood. Well, so the wood broke when it got down to 2 kilograms. The wood was the amount of deflection. I don't know if it broke or the amount of deflection was just too great per some standard or something. So that is the wood right there. The least amount of deflection appears to be occurring here with the I-beam, 0.35. Followed by the square steel, 0.82, followed by the flat, 2.9, followed by the wood again at over 6. So quite a bit of deflection. So the wood's in a whole other category than the steel. And then we could see, as the loads continue, we could see the amount of deflection. And that contributes both to the material and the shape. Okay? All right. So I think that covers it for now. So thank you.